All right, guys, here we go. So have you ever gone on a merry-go-round? Yeah. So if you are outside of that merry-go-round, then during like as time passes by, you're going to be going all around like that, right? So that's called the distance that you traveled. But if you go right in the center while the merry-go-round is spinning, then you don't travel any distance. You just spin. Does that make sense? So, by the way, angular velocity, anything dealing with rotation is angular velocity. So anything that rotates, anything that rotates. So an example is like degrees, degrees per second, or radians per second, or revolutions per minute. It doesn't have to be per minute, as long as it's some type of rotation divided by time. Yay or nay? And then linear velocity is the one that you guys have been doing all this time. Examples of that are like meters per second, kilometers per hour, miles per hour. So anything dealing with distance is linear velocity. Distance divided by time. I should be specific. Anything dealing with distance divided by time is linear velocity. And anything dealing with rotations divided by time is angular velocity. Does that make sense, guys? Okay. Now, R stands for radius, A stands for arc length, theta stands for the angle that you rotate, V is linear velocity, and this is called an omega. Yeah, omega. And this is what we use for angular velocity, and then T stands for time. And then, of course, why do they give you all that? So they can give you formulas, right? Notice we're not even going to talk, look, the radius. So we're going to say that 1 radian is equal to radius. So write that down. So 1 radian, when you hear 1 radian, you're talking about radius. And also the metric system. Do you guys know the metric system? Kilo, hecto, deca, base, deci, centi, milli. All right, so what does that mean? If I have 1 kilometer, I want to know how much that is in centimeters. Well, here's kilometer. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. Everywhere there's a little pivot, you put a 0, and there it is. That's how you use it. Do you guys remember that? So yeah, what does the K stand for? Kilo. The H, hecta. The D, deca. This is your base. Chop, what's a base? Like a meter, like a gram, instead of kilogram, gram, like your base. This D over here, these are now the smaller numbers. This is deci. This is centi. This is a milli. Milli. Just not confused with the rapper. And then, oh, you guys know what I'm talking about? Or maybe you guys are too young? Never mind. Okay. And then, of course, if you go another 3, it's micro, pico, all those. The way I have it here, smaller to the right, bigger to the left. Why do I write it like that? Some people write it the way that you just said. I like to just count, guys. I like to just count. So if I want to know like 1 kilometer in millimeters, I just count. I just go 1, 2, 3, 4, 5, 6. So here's my 1. There's that decimal. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And that's millimeters. See? Do you guys see how I'm using it? Okay. So that's how I use it. So make sure that before you graduate, guys, that you guys are pretty decent with the metric system, because you're going to be with other kids that are at the university that already, especially if they're coming from overseas, they've been doing the metric system since they were in elementary, right? Because that's what they use. We use the English system here, but then we teach you guys about the metric system. So, but same thing, guys. Real quick, do you know how many feet are in a mile? And there's others. I don't remember the centimeters to inch, 2.54 centimeters to inch, I think. I'm not sure. Don't quote me. The only reason I memorized this, do you guys remember a movie called Remember the Titans? No? Have you ever seen it? Denzel Washington, and it's a football movie. And there's this guy named Petey, and he drops a football during practice. And Coach Denzel goes, "How many feet are in a mile? How many feet are in a mile?" And then the player's like, I don't know, coach. And he's like, 5,280 feet. And you're going to run every single one of them. Something like that. And I don't know. I saw the movie and I just remembered. So I don't know. I'm not trying to tell you to watch movies to remember units, but find something to make sure that you know these little random facts. What's the speed of light? Okay, well, it's actually 2.99999 times 10 to the 8 meters per second. But okay. What's Avogadro's number? 6.02 times 10 to the 33rd. Okay. What else? What else do you need from? All right, let's just continue. Let's just do this. Turn the page, guys. There's formulas, and if you want me to teach you with formulas, I can. We can just say use your formulas, but I really don't want to go that route. So let's see how we do. So look at question number 1. It says an old long play record, as in the figure to the right, rotates at 33 1/3 revolutions per minute. So next time I'll push this record a little more to the right so the rev per minute can come out over here. But there it is, revolutions per minute. So this is an example of angular velocity. So it says find the angular velocity in radians per second. So all they want me to do is to translate this 33 1/3 revolution per minute into radians per second. So remember, in one revolution, how many radians are there? In one revolution, how many radians are there? 2 pi. Remember the unit circle? Oh, remember, one revolution is 2 pi radians. So put that down somewhere. 1 rev equals 2 pi radians. All right. Oh, by the way, 1 revolution is also, if you want to know the circumference, 2 pi r. That r is radian. See, radian. Okay. So hopefully you guys are seeing that now. All right. So I'm going to take the 33 1/3. So do you guys remember stoichiometry from chemistry? Okay. Relax. Look how easy it is going to be. 33 1/3 revolutions per minute. And I want radians per second. So let's see. In 1 revolution, how many radians are there? You guys just told me. So I'm going to write 2 pi radians. So there it is. Right now I have radians per minute. I don't want radians per minute. I want radians per second. So I'm going to write minute up here because that's what I want to cancel. And I'm going to put second down here. In 1 minute, how many seconds are there? 60. There it is, guys. Minutes cancel out. And look at your units. Radians on the top, seconds on the bottom. So you never get them wrong. What's up?
So minutes is on the bottom because I was divided by minutes.
Okay, say it again.
Minutes on the bottom on 33 1/3 because revolutions divided by minutes.
Revolutions in the bottom because I want to cancel the revolution.
No, I mean minutes under like right in.
Well, I had revolutions per minute, so I had to write the minute on the top so I can cancel the minute, right? And now it's revolution. Now it's radians per second, right? Okay. All right, guys. So you never get it wrong. Never, ever, ever get it wrong. Use this feature all the time. Focus, focus, focus. Alpha, y equals, enter. And you will never get it wrong. Whatever you have in the top is what you're going to write. Whatever you have in the bottom is what you're going to put in there. Chav, how do I type in 33 1/3? Like this. Push alpha again. Push y equals, and it's the number 2. And then you go 33 1/3 times what? Is it 2 pi? Times 2 pi. And I'm dividing by what? Just 60. So put a 60 in the bottom. Enter. And there it is. 3.4906585504. The more digits, the better. At least how many? At least 3 after the decimal. 3 point, and I already forgot. 490658. 490658. And I'm going to put units. Radians per second. Units are important here, guys. If you have units, put units. Are we okay so far? Okay. Let's go to the next one. Letter B. Find the angular and linear velocities of the record per second at the point which the needle is located when it is just starting to play 14.5 centimeters from the center. All right. So they want the linear velocity and angular velocity right over here at the 14.5 centimeter range, right at the edge of that needle there. So My angular velocity is the same. It's this up here. It's this number. You can also say 33 and 1/3 rests per minute. 3.490658 radians per second. You could have also said 33 and 1/3 revolutions per minute. They're all the same. They're both angular velocity. Are we okay? All right. Here's my preferred method for linear velocity. My preferred method, I take this guy right here and I go 3.490658 radians per second. Are we still okay? And I go in 1 radian. What's the radius? Not everyone at the same time. No, in 1 radian, not how many radians. What's the radius? 14.5 centimeters. This is my preferred method. I'll go over another method right now, guys, if you don't like it. 3.49065 times 14.5. 50.6145. and I already forgot. 61454831. 6145 centimeters per second. Chav, I don't like it. Can you show me another way? Yes. Do you remember when you were in geometry that the circumference of a circle is 2 pi r? Okay. You could have gone from that one. You could have said, okay, I guess you could have also, okay, don't write this down. I'm just showing you another way. There is a preferred method, but you could have said, okay, I'm going to go from here, Chav. And you could have gone 33 and 1/3 revolution per minute. And then in one revolution, you cover the circumference of a circle is 2 pi r. So in revolution, you cover 2 pi times 14.5 centimeters. That's how much distance that covers if you do 1 revolution. And then they want it in per second, and in 1 minute, there's 60 seconds. So if you think about it, it's really the same thing. See, look, there's your 2 pi times r. 2 pi times r, then 1 radian. In 2 pi radians is 1 revolution. So check it out. If I do this, I'll get that same answer. Watch. Alpha y equals, enter alpha y equals number 2, and 33 and 1/3 times 2 pi times 14.5. Let's see, what else do I have? 33 and 1/3, 2 pi, 1 minute, and then the bottom 60 seconds. Look, guys, 60 seconds. Same. Nothing changes. And if you think about it, we really just did the same steps we just did a little while ago. We're just 1 radian is your radius. Circumference of a circle, yes, is 2 pi radians, but that formula really is 2 pi r. That's really the circumference of a circle. You guys see what we're talking about? Okay. All right. No, don't worry, guys. It's gonna get easier. We haven't done anything crazy. All right. Fine. Oh wait, did I already answer the question? Okay. At which point are they located? Yeah, that's it. So radians per second, and they're both mean the same thing. And here is my linear velocity. Linear velocity. This also gives you 50.6145. Okay, here we go. Find the angular and linear velocities per second at the center of the turntable. Well, I guess this one was not per second. This was revolution per minute instead of per second. All right, angular velocity in per second is 3.490658 radians per second. Everywhere, at the center and, at the center. Okay, let's see how smart you guys are. At the center, even though that's how fast you're rotating, how much distance are you covering? Yeah, 0. You're just spinning. You're just spinning, guys. You're not covering any distance. You're just spinning. So 0, and then put units, centimeters per second. Does that make sense? Okay. All right, guys. I put the easiest examples that I could think of. Has everyone ridden a bike before? Okay, good. Because I was going to talk about axles and all that stuff connected. sprockets connected, wheels connected. But I was like, you know what? Let's introduce this with stuff that everyone has done. Here's a bike. I'm in the next page. It says the figure to the left shows the back wheel of a bicycle. A small sprocket is connected to the axle of the wheel. This sprocket is connected by a chain to the large sprocket to which the pedals are attached. So there are several rotating objects whose motions are related to each other. No. Demerit. Example 2. A cyclist turns the pedals of her bicycle at 8 radians per second. So I'm pushing down on these pedals at 8 radians per second. The front sprocket has a diameter of 20 centimeters. So let me zoom in. If the diameter is 20 centimeters, what is my radius? 10. That's what I care about. You care about the radius. Because 1 radian is 10 centimeters for the front sprocket. The radian can be different for different things, right? Because the radiuses are different all over the place. All right. And it's connected to the chain by the back sprocket, which has a diameter of 6 centimeters. Okay, so I'm going to zoom into the back sprocket. The back sprocket has a diameter of 6, so that means the radius is 3. Is everyone okay so far? The rear wheel has a radius of 35 centimeters and is connected to the back sprocket. Okay, there it is. So I'm going to do from the center to the back of that wheel all the way there. How big is that? Not everyone at the same time? It is 35 centimeters because that's what it says, that the radius is 35. Are we okay, guys? Okay. What is the angular velocity of the front sprocket? All right, let's think about it. Angular velocity. The pedals are connected to the front sprocket. So if the pedals are going 8 radians per second, if the pedals do 1 revolution, so does the front sprocket. So radians per second is angular velocity. So if the angular velocity of the pedals is 8 radians per second, so is the front sprocket. So there it is. 8 radians per second since pedals are connected to front sprocket. Chav, what does that mean? That means if pedals do 1 revolution, so does front sprocket. Yep, it works. Makes sense. Does it make sense to you guys? If pedals do 1 revolution, that's 1 rev, so does front sprocket. That makes sense, guys? Okay. Let me know if I'm going too fast. Am I going at an okay speed? Okay. All right. Letter B. What is the linear velocity of points on the chain? So they want to know how fast the chain is going. I'm going to zoom in. They want to know the chain is right there at those dots on the front sprocket. They want to know how fast that chain is going. Well, I know how fast that chain is spinning right there at that location because of the front sprocket. Does that make sense? I guess technically the chain's not spinning, but the front sprocket is, and I know how fast the front sprocket is spinning. So I'm going to take the angular velocity of the front sprocket and I'm going to turn it into a linear velocity. So here we go. I'm going to go 8 radians per second. And I know that linear velocity has to be in centimeters per second. So I'm going to say in 1 radian, how many centimeters do I have for the front sprocket? What's my radius? 10 centimeters. So there it is. Radians cancel out. 8 times 10 is 80. So that chain is moving at 80 centimeters per second. Do you guys see how we did it? Okay. How do we feel so far right now? All right. I think we're winning. I think we're good, guys. All right. Let's keep going. Letter B. What is the linear velocity of points on the rim of the back sprocket? All right. Think about it, guys. They're not trying to trick you. They want to know the linear velocity of points on the rim of the back sprocket. Is that sprocket connected to the chain? How fast was the chain going? So is it going 80 centimeters per second right here? Yes, it has to. It's connected by a chain. It has to. The chain. If you're not going 80 centimeters per second right there at the edge of that back sprocket, then that chain is falling down. Do we get it, guys? So it has to. It's connected to the chain, guys. So we're gonna say, what is the linear velocity points to the rim of the back sprocket? 80 centimeters per second. And then I'm gonna put in parentheses, connected to chain, comma, hence, comma, it must be the same linear velocity as chain. Does this make sense? Okay, always ask yourself if it makes sense, guys. All right, let's go to the next page. It's still the same thing. It's still dealing with that same bike. So let me go ahead and write it in here that this radius is still 10. R equals 10 centimeters. This little r there is still 3. And this big R here is still 35. All right. Let's see what it has. Let's see what it asks. What is the angular velocity of the center of the back sprocket? Now it wants to know how fast the back sprocket is spinning. Because it's smaller, it's spinning faster. So I'm going to take my linear velocity, 80 centimeters per second, and I'm going to convert it to angular. For the back sprocket, what's my radius? So in 1 radian, there is 3 centimeters. And there it is, radians per second. Take your calculator, go 80 divided by 3. 80 divided by 3. There it is, 26.666. 26.667 radians per second. And guys, okay, catch up to here. All right, let me see if I can explain this. That's not the only way. You could have also done it. Look what you could have done. You could have done it with geometry, with scale factors. You see this and you see this back sprocket? They're both connected by a chain, right? So I'm going to figure out the scale factor for this. See, the radius is 10. I'm going to figure out the scale factor between the big one and the little one. So I'm going to go 10 divided by 3. This is from geometry. Child, what are you doing? I'm trying to show you guys another way to get this answer. Look at this. Check it out. I'm going to go to here, and I'm going to go 10 divided by 3. And I get this number. What does that mean? This number means that every time the big one does 1 revolution, the little one does 3.333 revolutions. Does that make sense? So I bet you, look, remember I have the speed in radians per second for the front sprocket. So I bet you if I take the speed for the front sprocket and I multiply it by that number, I bet you I'll get the same answer. Let's see. What was the speed of radians per second for the front sprocket? Was it 8? Look, times 8. Look at this. OMG. The same thing. Do you guys see that? Okay, put in there, put a side note, a second way. The second way to get this answer is, put in there that you got the scale factor. Put in there that you got a scale factor, and that all we did was multiply by the scale factor. I'll put it here for you guys too, if you guys want to see it. I'll put in, let's see, what am I going to do? 10 over 3 equals 3.333 scale factor. So, small bracket, omega equals 3.33 times 8. That's your scale factor. And we got 26.667. And I will put it in words what we did. You know, we found scale factors since they're connected by the link. That 3.33 means for every 1 revolution the big one does, the little one does 3.33 revolutions. Notice that They've been telling us angular velocity, but we have not been given it. We've just been doing radians per second, but you can choose revolutions per minute if you want. Does that make sense, guys? Has all this made sense? Okay. Are we good? All right, here comes my favorite part. So look at this question, guys. It says, how fast is the bicycle going in kilometers per hour? So check it out. Do you agree? So before we even get to master this question, do you agree? And make sure that it makes sense to you. Assuming that you're pedaling, I know you can just idle. If this little back sprocket does one revolution, does this big wheel do one revolution? No? If this little back sprocket, this is the chain. If this little back sprocket does one revolution, this little wheel does one revolution. Because it's part of the bike. That's how it works. Right? So there it is. So that's the key. Don't we have the angular velocity for the back sprocket? Turn the angular velocity of the back sprocket into a linear velocity. But this time, 35 centimeters is 1 radian because that's what my radius is. That's what's touching the ground. Does that make sense, guys? So here we go. So we're going to come back and I'm going to say, all right, start with the radians. 26.667 radians per second. And in 1 radian, there is 35 centimeters. Are we still okay, guys? Okay, so right now I have centimeters per second. That's not what I want. I want kilometers per hour. So then we're going to go, let's see, what am I going to do? I'm going to turn the seconds into hours, guys. So I'm going to put a second up here, and I'm going to put an hour down here. In 1 hour, there's 60, in 1 hour. Let's do minutes first. I was going to say 3,600, but let's just go let's go slow. In 1 minute, there is 60 seconds, and I'm going to cancel out the seconds. So I'm going to put, I already canceled out the seconds. I'm going to cancel out the minutes. I'm going to put the minutes on the top and an hour on the bottom. In 1 hour, there is 60 minutes. So look, seconds cancel out, minutes cancel out. So right now I have centimeters per hour. I already took care of the hour. Now I got to take care of the centimeters. Remember your metric system, guys. Kilo, hecto, deca, base, deci, centi, milli. In 1 kilometer, there is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 100,000 centimeters. If you knew that already, you could have just gone 0.00, whatever the number, right? 1, 2, 3, 4, 5, 0.00035 centimeters. Okay, here we go. I'm going to write 100,000 centimeters here. And I'm going to write 1 kilometer up here. So you never get it wrong. Use that feature that I just told you about on the calculator, guys. So let's see what that is. I'm going to go alpha y equals enter. And I'm going to go 26.667, so enter, times 35 times 60 times 60, times 35 times 60 times 60. And on the bottom, I'm going to put 100,000. I'll lower it somewhere. Push enter. And there it is. 33.6 kilometers an hour. 33.6 kilometers per hour. About, hey Siri, how much is 33.6 kilometers per hour in miles per hour? 20.88 miles per hour. Thank you.
Sure.
I shut it before it said it. Sorry, Siri. Okay. It didn't give me one more digit. Should have given me one more, but that's fine. And there it is, guys. That's pretty fast for a bike. That's pretty fast. What do you guys think? Okay, we're going to do one more. I'm going to do the hardest one we have here, guys. So go to the activity. We're going to do the hardest one, and the other 3, compared to number 2, are relatively simple. So all you got to know for number 2, because eventually you're going to get there, how many feet are in a mile? How many feet are in a mile, guys?
5,208.
Good job. How'd you guys know that? I'm kidding. That was a joke. From listening. All right. The blade on a rotary lawnmower is 19 inches long. Oh, okay. So we're talking about a lawnmower here. The cutting edges begin 6 inches from the center of the blade. See if you figure to the right. In order for a lawnmower blade to cut grass, it must strike the grass at a speed of at least 900 inches per second. Oh, okay. That's cool. If you want the innermost part of the cutting edge to cut grass, how many radians per second must this blade turn? How many revolutions per minute is this? Okay, so they're asking two questions. Let's do this one first, and then we'll do that one second. How many radians per second is this? Start with the 900 inches per second. 900 inches per second. This is just like stoichiometry. Are we still okay? What's up? I didn't give you one? All right. From there, how many inches in a radian? Because they want the innermost part to cut. So they're talking about this distance right here. So what is that distance? What is that radius, quote unquote? Yeah. So I'm gonna write 6 inches in the bottom. I'm about 1 radian in the top. So there it is. This is in inches per second. That's what they wanted, right? Inches per second. So I'm gonna go 900 divided by 6. 900 divided by 6. Enter. And there it is, 150. So I'm gonna type 150 radians per second. So there's one answer. Are we still okay? All right, here's my second answer. I'm gonna go to blue. It wants to know how many revolutions per minute is this. So I'm gonna go 150 radians per second. And I'm gonna put radian in the bottom and revolution on the top. In one revolution, how many radians do I have? 2 pi. All right, be careful with this one, guys. Some of you are going to do 150 divided by 2 times pi. Some of you are going to do this. Tell me why this is wrong. Because the calculator thinks you're doing 150 divided by 2 and whatever that is times pi. So you got to put parentheses, guys. By the way, I just noticed that I didn't convert this. It's still in seconds. They wanted it per minute, no? Okay, so we still don't have the answer then. Right now we have revolutions per second, which, by the way, is pretty fast. Look, we got it right here. 23.87 revolutions per second. So just multiply that by 60, or just do the dimensional analysis. So look, in 60 seconds, there's 1 minute. And look, you got revolutions per minute. So 150 times 60 divided by 2 pi. So I'm going to do alpha y equals enter. And then there it is. So you'll never get it wrong, guys. Never, never, never. 150 times 60. And then divided by 2 pi. There it is. 1432.394488. 1432.394488. 394488. Revolutions per minute. Always put units whenever there's units. Are we okay? Lopez, are we okay? Okay. All right, guys, try and focus, guys. Try not to be on your phones because, you just step away for a little bit and you get lost real quick. All right. What is the linear velocity of the outermost tip of the blade while it is turning as in part A? So now they want to know the linear velocity of the outside right there, of that tip right there. So I need to know what the radius is from here all the way to the outside. So 19, divide that sucker by 2. What's 19 divided by 2? 9.5? 9.5 inches. That's my radius, guys. Are we still okay? So here we go. Ready? This is how fast I'm spinning. You know what? Let's go from the 150. You could have always gone from the revolutions per minute, but I'm going to go from the 150. I'm going to go 150. That'll turn to red. 150 radians per second. And this time, 1 radian is 9.5 inches. And there it is in inches per second. So I'm going to go 150 times 9.5. And there it is, 1425. So 1,425 inches per second. Are we still okay, guys? Yes, ask me. Oh, because they said linear velocity. So I need to have distance divided by time. And so I need to have either inches. It doesn't have to be seconds. It could be inches per minute. It can be inches per hour. But I need to have distance in the top and time in the bottom. So inches per second. What's up? A radian is literally the radius. But remember, one revolution is also 2 pi radians.
So the radius. Okay, it's just the radius.
No, 1 radian. If you say 1 radian, it's just a radius. Yes.
Oh, okay.
Yes.
So it's no difference between radian and radius.
Radian is radius. Okay. Are we okay so far, guys? Okay, give me a little more. Don't worry, we're almost there. Letter C. If the outermost tip of the blade strikes a stone while it is turning, as in part A, how fast could the stone be propelled from the mower? How many miles per hour is this? Assuming it does not lose energy. Come on, Lopez. Assuming it does not lose energy, it's going to be this distance, 1425 inches per second. Does that make sense? Okay, now how fast is this in miles per hour? So you're going to go 1425 inches per second. And I'm converting this to miles per hour, guys. So let's do the seconds converting to hours real quick. How many? So I'm going to go seconds to minutes. So I'm going to put seconds here, minute here. And I'm going to go minute to hour. So I'm going to put minute up here, hour here. Okay, in 1 minute, there's how many seconds? 60. And in 1 hour, there's 60 minutes. So there it is. We've taken care of the seconds. We have hour in the bottom. But now I want the inches in the top to turn into miles. So I have to go from inches to feet to miles. Does that make sense? How many inches in a foot? So I'm going to write 12 inches down here because I want to cancel it. 1 foot on the top. Now I want to cancel out feet. How many feet are in a mile? There it is, 5,280 feet. And look, feet cancel out, inches cancel out, and you just have miles in the top and hours in the bottom. Take your calculator. Go alpha y equals enter, and then type it in. So 1425 times 60 times 60. 1425 times 60 times 60. And on the bottom, we're going to go 12 times 5280. 12 times 5280. And look, oh, okay. Now what? Child, what do? Just type it in again like this. You can also tell the calculator to give it to you in decimal by going to the mode. But this is good enough. And look, 80.9659. What are my units? 90. So, yeah, miles per hour. 9659. Miles per hour. Is that pretty fast? Okay, next time you guys go mow the lawn or whoever, wear protective gear, wear glasses, because if a rock hits you in your eye socket, say bye to your eye. That's pretty fast, guys. You're not going to have an eye if you get hit in the face with that. So whoever cuts the lawn, whoever mows the lawn, tell them to wear, tell them, and tell them, like, as a matter of fact, be blunt. Dad, I did the math. Look, here it is. Show them this. It's going to come out at 80 miles an hour if a rock hits you and if it hits the edge of that blade. So wear these glasses. Wear something, guys. Okay, that was the hardest question in here. So I think you can take care of 1, 3, and 4. Every class so far, for the most part, has turned it in. Not everyone, but close to 100% of them. So I think you guys can too. So let's take care of business, and we're done, guys. You can work in groups. What do you guys think? Was this pretty cool?